Hi everybody! In section 12.3 we are going to go over the dot product. So what is the dot product? Well, last section we talked about vectors in general in 12.2, and in that last section we talked about vector addition. So we took some vector A and we added to that vector B. We also talked about the scalar multiple. So we took some scalar, which we can call C, and multiplied it by some vector, and saw how this affected the vector, multiplying by a positive scalar, multiplying by a negative scalar, and we saw that this just changed the direction and magnitude of this vector. So that's what we did last time. Now we're going to talk about something a little bit different. The dot product is a way that we can multiply two vectors of the same size. Now, I say it's a way that we can multiply two vectors because there are different ways that we can multiply two vectors, and in fact next week we're going to be talking about the cross product, which is another multiplication technique, and it just gives us a little bit of a different set of information geometrically. So this is a way that we can multiply two vectors A and B. Note the vectors must be the same size to take the dot product of them. And when we multiply using the dot product of this A and B, we find that we're taking the first component of A and multiplying it by the first component of B. Now, in this form, remember, we're not using that I, J, and K notation, so A1 and B1 are just numbers, right? And then we're adding to that the second component of each of these vectors, and adding to that the third component of each of these vectors. And because all 6 of these components are just numbers, when we multiply two numbers, add to that the product of two numbers, and add to that the product of two numbers, now we no longer get a vector. We don't have 3 terms anymore, now we just get one number. So we can say that the dot product of A and B will give us a scalar. And that's why a lot of times this can be called the scalar product, because it tells us that now when we take the dot product of A and B, we're not spitting out another vector, we're just spitting out a number, a scalar. So there are a few rules here for dot products. A few properties of dot products, and these are going to be similar to what you know about properties of multiplication in general. So just like when we multiply some variable by itself, we get that variable squared. Now here we have the magnitude of A squared, that the dot product of A with itself is the magnitude of A squared. The distributive property does apply for the dot product. Because it's a product, if we multiply some vector A by 0 using the dot product, we get 0. Anything times 0 is 0. The dot product does hold the commutative property, meaning that we can switch around the order of A and B, and the dot product will yield the same results. And finally, we have the associative property of multiplication that holds true with the dot product of A and B times a scalar C. Alright, now one thing that we can't do is that we cannot take the dot product if A and B have different dimensions, or if we have a scalar, we cannot take the dot product of a scalar times a vector. So we can't do something like this. So we cannot take some A1, B1 times B1, B2, B3. So if these vectors are not the same size, we cannot take the dot product. We also cannot take the dot product of a vector times a scalar. Notice that we can multiply a vector times a scalar. We can absolutely do that. And we talked about that last week. We can multiply some C by a vector. However, we cannot take the dot product of a vector and a scalar. So dot product is just a little bit different than multiplying. So let's do a few examples of the dot product. So if we want to take the dot product of 2 and 4 and 3 and -1, our rule states that we are taking the first components and multiplying them together. First component of the first vector is 2. First component of the second vector is 3. So we're multiplying the first components of each vector, and we're adding to that the product of the second components of each vector. So we've got 4 and -1. Simplifying this, 2 times 3 is 6. 6 plus -4 becomes 6 minus 4, which is 2. And so the dot product of these two vectors is just the scalar 2. And we're going to make sense of this soon. Let's just get the method down first. So the dot product, now we have vectors with 3 dimensions, with 3 different components. And again, we're taking the first components of each of these vectors and multiplying them. So we've got -1 and 6 plus 7 times 2 plus 4 times 1/2. Simplifying this gives us -6 plus 14 plus 2, which is 16 minus 6, which we can simplify to be 10. Now this third example, it looks a little bit different, but we're doing the same thing here. However, because we have a little bit of a different notation, let's write this in this classic vector notation so we can more clearly see each of our components. So I know that I can rewrite I plus 2j minus 3k as 1, 2, -3. And I can rewrite 2j minus k, and in this case I don't have an I component, so I'll put a 0 as the placeholder for the I component. 2 for that j component, and -1 for that k component. And now we can see that we are taking the dot product of 2 vectors of the same size. Now if I forgot that there was really a 0 placeholder for this I here, because we really have 0I plus 2j minus k, then that might look like I'm taking the dot product of vectors with a different size. But in fact we are not. So just make sure if you have a vector written in this I, j, k form and you're missing some of the components, that you put that 0 placeholder in so you can do that multiplication. Alright, so now let's take this dot product. Now we're taking the first component of the first vector, multiplying that by the first component of the second vector. So that gives us 1 times 0 plus the second component of the first vector times the second component of the second vector, and plus the third component of the first vector times the third component of the second vector. Simplifying this gives us 0 plus 4 plus 3, and so our dot product yields the scalar of 7. So now that we've gone over the method for computing a dot product, let's talk about what this actually means geometrically. So geometrically, the dot product can be given in terms of this angle theta. And we just use the origin as a starting point because it's a little bit easier, but remember now, it does not matter where vectors originate, it just matters what their magnitude and direction is. However, if we say that 2 vectors are coming from this origin here, we've got an A, we've got a B, then the angle between them is theta. Then we can say that the dot product of A and B is equal to the magnitude of A times the magnitude of B times the cosine of theta. Now, what does this really mean? This is, a great formula, but what this does is it applies the directional growth of one vector to another. It's saying if I take this vector B and I use the dot product to multiply it by vector A, what does that do to vector B? How much stronger are we making this vector by multiplying it by A? Now, with this formula, we can rearrange it to get the cosine of this angle theta if, we're given the dot product but don't have this angle and we're looking for this angle. So we can just rearrange these formulas. And before we move on, let's look at kind of a more real-world example of what the dot product really is. So I found this example of what a dot product is using the Mario Kart Speed Boost, and I really love it. So if anyone has played Mario Kart, you know that you're a character and you want to hit these boost pads because these boost pads increase your speed in some certain direction. It's not necessarily straight, and if you can kind of see on this course, it looks like the boost pad pushes you a little over here to the right. Now I'm not sure exactly what the path is. So imagine this red vector is your speed in the x and y direction. So you're coming in at a certain speed with a certain direction. Well, that sounds a whole lot like you could describe that as a vector if you have a speed, a magnitude, and a direction. And the blue vector is the orientation of the boost pad, meaning that's going to be, let's call that our vector B. So if we call this red vector A, this blue vector B, well, how much boost do you actually get from it? So what's the actual trajectory of Yoshi in this case? Well, that comes from the dot product of A and B. Now, a couple rules here, and this applies to the rules that we know about dot product. If you fall on a boost pad, I don't know if you've played as much Mario Kart as I have, but if you fall on a boost pad, you come in with 0 velocity, you will get 0. This boost pad will not help you out if you're not going in with any kind of velocity. If you cross this boost pad perpendicularly, you will also get 0 boost. And you know, the way this relates to our equation is that if our angle is 90, if we come in perpendicularly, well, the cosine of 90 is 0. So we'll get 0 boost. However, we can look at it as, you know, the total outgoing speed is the speed in the x direction times the boost in the x direction plus the speed in the y direction times the boost in the y direction. And this will give us the total speed you actually leave with. So just another way to look at this to kind of show us how the dot product is really just the directional growth of one vector applied to another. So let's do a few examples. Example 2, if the vectors A and B have lengths 4 and 6 and the angle between them is pi over 3, find the dot product of A and B. So I know that my formula is the dot product of A and B is equal to the magnitude of A times the magnitude of B times the cosine of theta. So if these vectors have lengths 4 and 6, well, what is length but really a magnitude? So I know that the magnitude, I'll call this of A, is 4. The magnitude of B is 6. And it doesn't matter which of these vectors A and B we call the one with a length of 4 and the one with a length of 6, because we remember that the dot product of A and B is the same as the dot product of B and A. All right, and the angle between them, our theta, is pi over 3. Then find the dot product of A and B. Well, we have everything we need to solve this right side of the equation. And so we get the dot product of A and B is equal to 4, the magnitude of A, times 6, the magnitude of B, times the cosine of pi over 3. All right, the cosine of pi over 3 is 1/2, and so the dot product of A and B is 24 times 1/2, which is 12. All right, simple enough. Example 3, now we're going to find the angle between these two vectors. And we can rearrange this formula because we're looking for this angle to be that the cosine of theta is equal to the dot product of A and B over the magnitude of A times the magnitude of B. Now if we want the angle between these two vectors, we don't want the cosine of theta. That won't really help us out much. We just want theta. So we can find theta by taking the arc cosine of everything on the right side of this equation. Just manipulating this one equation to find what we're looking for. And me personally, I don't memorize all these different equations. I just memorize this equation, just kind of using what I know about the definition of a dot product, and then we can derive, anything else we might need. So with this, we are looking for the dot product of A and B. We also need to find the magnitude of A and the magnitude of B. So let's find all this stuff separately. So to find the dot product of A and B, we are taking the dot product of 2 to -1 and 5, -3, 2, meaning we are taking the first components and multiplying them. So 2 and 5, adding to that the second components which we are multiplying, and adding to that the third components. All right, we've got 10 -6 -2, and so our dot product yields 2. All right, our dot product of A and B. Now we need to find the magnitude of A. We remember the magnitude of a vector is just the square root of all of its components squared. We add those components together, so we are taking 2, squaring it, adding to that 2, squaring it, the second component, and adding to that -1 and squaring it. We can simplify this. This is the square root of 4 plus 4 plus 1, and we know that the square root of 9 is just 3. Let's do the same thing to find the magnitude of B. That's going to be the square root of 5 squared, taking all these components, plus -3 squared, plus 2 squared, which gives us 25 plus 9 plus 4. All right, that gives us 38. And we cannot simplify 38. All right. So now we have everything we need to find this theta. So our angle theta is the arc cosine of this expression. Now our numerator is just 2. We found the dot product of A and B to be 2. In the denominator, we just have the magnitude of A times the magnitude of B. Let's go to our calculators to find this angle. When we calculate this, we get that our theta, our angle, is approximately, I'll round to the nearest tenths, 83.8 degrees. You could also use radians for this. Your homework will be a little more specific on if they want you to use radians or degrees. All right, one more example. Find the acute angle between the lines. Now this might seem a little bit strange because in this case we're just given 2 linear equations. We're not given vectors. But we know that these methods work for vectors, so we're going to convert these equations to vectors. So let's take 3x minus y equals 3. Well, how in the world do we convert this to a vector? Well, we know that a vector just contains magnitude and direction. Because this is a line, it has no beginning and end. And we're just looking for the angle here, so the only thing we're really worried about is that direction. And how do I find the direction of a line? Well, I know that direction is the slope. So I'll rearrange this in slope-intercept form. And I get y, if I add y to both sides, is equal to 3x. And then if I subtract 3 from both sides, we get y is equal to 3x minus 3. This tells me that my slope is 3. Now let's remember what slope really is. Slope is really the rise over the run. Another way we can put that, it is the change in y over the change in x. And that's kind of helpful because we remember what a vector is. Our different components of this vector, and I'll call this vector A, just to give this a name. I am going to have the change in x, comma, the change in y. And the change in y is going to be 3. In this case, we can write 3 as 3 over 1. So I can write this as a vector of 1, 3. Because this says that for every 1 unit I go to the right, I go 3 units up. And isn't that exactly what slope does? This directional vector just tells me that essentially we have a slope of 3. And we're assuming we're in 2 dimensions here because we're only using the x and y variables. So now let's do the same thing for the second equation. 5x plus y is equal to 7. By subtracting 5x from both sides, we get that y equals negative 5x plus 7. And so our slope is negative 5, or negative 5 over 1. Because we have our slope, we can call this vector, I'll call it b, is equal to the change in x, comma, the change in y. Just breaking this up into their vertical and horizontal components. So now we've got 2 vectors. Now we can use what we know to find the acute angle, and we'll settle this acute part a little bit later. But we know we're going to use, let's see, to find this angle, this version of the formula. Theta is equal to the arc cosine of the dot product of A and B over the magnitude of A times the magnitude of B, just because we're solving for that angle again. So let's find this dot product. A dot product B is equal to, well, I'm multiplying 1 and 1, and I'm adding to that 3 and negative 5. All right, 1 minus 15 is negative 14. So we have our dot product. Now for our magnitude of A, our magnitude of A is going to be the square root of 1 squared plus 3 squared, which is the square root of 10. And the magnitude of B is the square root of 1 squared plus negative 5 squared, which is the square root of 26, neither of which can be simplified. So let's find that angle. Plugging these values into our formula, let's go to our calculators and see what we get. All right, calculator says this angle is about, and I'll just round to the nearest tenth, just because this is an intermediate step here, so 150.3 degrees. But now we want to find the acute angle between the lines. And if I have an intersection of 2 lines, remembering that acute just means less than 90 degrees, then I know that these two angles that are opposite are vertical angles. They're identical. These two angles that are opposite are vertical angles, also identical. Now I know that this angle and this angle has a sum of 180 degrees. So if I found that one of the angles between the intersection of two lines is 150.3, then I can find that acute angle by just subtracting this from 180. So say I found this was 150.3 degrees, then I can find this angle by subtracting from 180. And I get that that acute angle is going to be 29.7 degrees. And we can call that angle, let's call it alpha. Because now we're rounding to the nearest degree, we can say that alpha is 30 degrees. And so this angle would be 29.7, or approximately 30 degrees. So our acute angle is approximately 30 degrees. So now a little bit about orthogonal vectors, and orthogonal really just means at a right angle. So perpendicular. All right, so perpendicular vectors. Two non-zero vectors are perpendicular if the angle between them is pi over 2 or 90. And that's because we have this formula for the dot product. We know that the cosine of 90 degrees is 0, so it doesn't matter what the magnitudes of A and B are. If these are positioned perpendicularly, so if the angle between them is 90 degrees, well then that dot product is just going to be 0. Also, if the dot product of A and B is 0, then we know that the angle between these is 90 degrees. And so that's where we get this if and only if statement. And we can abbreviate this IFF. This is this if and only if notation. Just a little bit of a side note about this, because I know I went through this a lot in my math career in a lot of different proof classes, discrete math, things like that. What this means is that it's bidirectional, meaning that two vectors A and B are orthogonal if the dot product of A and B is 0, and it means if the dot product of A and B is 0, then two vectors are orthogonal. So this goes in both directions. It means by finding either sides of this statement, you can assume the other. It is not one directional. All right, so what does that mean? Well, it means we now have a method of easily determining whether or not two vectors are orthogonal or perpendicular. So let's talk a little bit about these angles. So we remember that with the dot product, we're really applying the directional growth of one vector to another. If we have an acute angle and we apply the directional growth of B to A, and they're facing in the same direction, if it's an acute angle, that means they're facing in the same direction, well then this change is going to be positive. Kind of like with the Mario Kart example, if we are facing in the same direction of the boost, we're going to go faster. If we are at 90 degrees, we said this cosine of pi over 2 is going to be 0, so this dot product is going to be 0. And if we have an obtuse angle, well, we know the cosine of an obtuse angle is negative, so this dot product is going to be negative. And if you are for some reason driving backwards on a Mario Kart course in the opposite direction of the boost pad will actually slow you down. I'm so sorry if you don't play Mario Kart. I know we're using that reference a lot here. But another way we can look at this is we can think of the dot product of A and B as measuring the extent to which A and B point in the same direction. So if this dot product is positive, great, they pointed in the same direction. If dot product is 0, they're perpendicular. If dot product is negative, they point in opposite directions. And if this angle is 180 degrees or pi, that means that A and B are completely pointing in the opposite direction. And in this case, the cosine is going to be 1, and the dot product is just going to be equal to the product of the magnitudes of A and B. All right, so let's do one more example of this. So we want to show that 2i plus 2j minus k is perpendicular to 5i minus 4j plus 2k. Well, two vectors are orthogonal or perpendicular if and only if the dot product is 0. Meaning that let's take the dot product of these two vectors, see if it's 0. That will help us determine whether or not they are perpendicular. Let's write this in that other vector notation. So we're going to call this first vector 2, 2, negative 1. We know we're going to take that dot product with this second vector, which we can write as 5, negative 4, 2. Taking that dot product, we're multiplying the first two terms, and I'll just do a little shortcut here. I know 2 times 5 is 10. We're adding to that the product of the second terms. 2 times negative 4 is negative 8. And negative 1 times 2 is negative 2. Since 10 minus 8 minus 2 is 0, that tells me that the dot product of these two vectors is 0. Then I can assume that these two vectors are perpendicular. So yes, they are perpendicular. And taking the dot product and showing that it is 0 is sufficient to determine that they are certainly perpendicular. Direction angles and direction cosines. So if we're looking at the first octave, where the x, y, and z values are all positive, we have these three different direction angles. So if we have any vector in the first octave, the angle between this vector and the x-axis is alpha. The angle between this vector and the y-axis is beta, and the angle between this vector and the z-axis is gamma. So we have what are called these direction angles, alpha, beta, and gamma. Now how do we find these? Well, we can find them using our directional cosines or direction cosines, however you want to say that. So we have this formula here, and where does that come from? Well, we said in the previous section that the cosine of theta is equal to the vectors A and B, the dot product of those two vectors. And I know sometimes I forget the vector notation when we're running through a lot of calculations, but just to be clear, these are two vectors divided by the magnitude of these vectors. All right, so this is our formula that just kind of shows us what this dot product is. Now, this is the same exact formula, except in this case we're looking at the vector I, because remember, I is just the unit vector in the x direction. So if we have our three-dimensional coordinate system, we have z, y, and x. I is just a unit vector of length 1 in the x direction. So what we're really doing is we're taking this same formula, but we're saying, okay, for alpha, which is the angle between this vector and the x-axis, to find this angle, we are just going to use the dot product between this vector and I, our unit vector in that direction. Now, because a unit vector has a magnitude of 1, that's the definition of a unit vector, this I just becomes 1. And because I is really, let's write this at the top, I really looks like the vector 1, 0, 0. So you can see that when we take a dot product of A, which can be broken down in three components, A1, A2, A3, and we take that dot product with I, we can see what happens. We're taking A1 times 1, adding to that A2 times 0, and adding to that A3 times 0. And all we're left with is the first component when we're talking about this alpha. Now with beta, we're doing the same exact thing, except with this unit vector j. With gamma, same thing, except with this unit vector k. So while this might look a little bit strange, there's nothing new here. We've got the same exact formula, but we're just simplifying it because now we just want to know the directional cosines and angles of this vector with the unit vector. These directional cosines just give us essentially the contributions of each component to that unit vector. So let's look at an example. Find the direction cosines and angles of a vector A is equal to 1, 2, 3. All right, well, direction cosines, we're going to have three of them. We're going to have these three direction cosines, alpha, beta, and gamma. So let's start with alpha. Well, we know that the cosine of alpha is equal to the first component of A divided by the magnitude of A. The directional cosine of beta is equal to the second component of A divided by the magnitude of A. And the cosine of gamma is equal to the third component of A, again divided by the magnitude of A. All right, let's start by finding the magnitude of A. The magnitude of A is just going to be the square root of 1 squared plus 2 squared plus 3 squared. The square root of 1 plus 4 plus 9 is 14, and so the magnitude is the square root of 14. To find these directional cosines, we are simply placing the first component in the numerator over the magnitude of A, which is the square root of 14. And we don't really need to worry about rationalizing our answers here. We can keep a square root in the denominator. That is just fine. The directional cosine of beta is going to be the second component divided by the magnitude of A. And the directional cosine of gamma is going to be the third component, again divided by the magnitude of A. All right, so these are our directional cosines. So how do we find the direction angles? Well, just by taking the arc cosine. We can find alpha by taking the arc cosine of 1 over root 14. And this will give us about 74.5 degrees. All right, beta is the arc cosine of 2 over root 14. Which is approximately 57.7 degrees. And finally, gamma is the arc cosine of 3 over root 14. Which is 36.7. All right, so these three (74.5, 57.7), and 36.7. These are the direction angles. All right, one more idea here. This is kind of an extension on the same idea from the direct cosines. These are projections. So if we have some vector b and we have some vector a, and we can imagine that we have a sun. And this sun is shining down on this vector b. Well, the shadow of vector b onto the ground, which goes from P to Q, is going to be PS. It's going to be this projection of B onto A. And so this is what a projection is. You can think of it as a shadow of B onto A. And so this is very similar to what we did with those directional cosines, but now instead of limiting it to each vector's contribution to the unit vector, now we can take into consideration different vectors other than just those three axes. So we have this scalar projection of B onto A. It's sometimes called the component of B along A, is the magnitude of this vector projection. So with this example, this projection would be that vector, and then the magnitude of that projection would be the component. So where does this equation come from? Well, that comes from our triangle geometry. If I'm looking at this triangle right here, I know that the cosine of theta is equal to the adjacent side length, which I can call PS, or the component of B onto A, divided by the length of this hypotenuse. And the length of this hypotenuse is just the magnitude of this vector B. And now by multiplying this magnitude of B to both sides, we can get that the component of B onto A is equal to the magnitude of vector B times the cosine of theta. Now one more thing we have to remember. Remember that equation, let's see, the dot product of A and B is equal to the magnitude of A times the magnitude of B times the cosine theta, right? So we have this formula here. Well, I can also say that magnitude of B times the cosine of theta is equal to the dot product of A and B divided by the magnitude of vector A. And so that's where this equation comes from. Just by using this equation right here, you can rewrite the component of B onto A is equal to the dot product of A and B divided by the magnitude of A. And these are all really vectors. Okay, that's where this component equation comes from. Now how about the projection? Because remember, the component's just the magnitude of that projection. So it's just the length of this arrow. All right? Now for the vector projection, all we're doing is we're taking this component, we're taking the magnitude and multiplying it by the unit vector, by this A over the magnitude of A. And that's how we get this actual vector. All right, so let's do an example. So we want to find the scalar projection and the vector projection of B onto A. So let's start by finding the component. So the component of B onto A, and just try not to confuse these, it's the component of B onto A. So whatever's in bold here is the of. This little subscript is the onto, so the component of B onto A is equal to the dot product of A and B over the magnitude of A. So let's find the dot product of A and B. We're taking the dot product of -2, 3, 1, and 1, 1, 2. Taking that dot product, we get -2 times 1 plus 3 times 1 plus 1 times 2, which gives us 3. Now we need the magnitude of A, which is equal to the square root of the quantity -2 squared plus 3 squared plus 1 squared, which is the square root of 14. So the component of B onto A is equal to 3 over root 14. And this is the scalar projection. So this is the length of this vector. This is the magnitude of that vector. Now to find the vector projection, we are simply taking the scalar projection and multiplying this by the unit vector of A over the absolute value of A, and these are both vectors. You know, it's difficult to write in boldface. And I'm just using parentheses because we generally use the multiplication symbol. However, we don't want to confuse multiplication with dot product because they are different. Because remember, this is a scalar. This vector A is a vector, and we said we can't take the dot product of a vector and a scalar, but we can multiply a vector by a constant, which is really what's happening here. And so we are taking 3 over root 14 and multiplying that by this vector A of -2, 3, 1, divided by the magnitude of A, which is again root 14. And this is going to be equal to, now when we multiply a scalar and a vector, we're really just using that distributive property. So this new vector becomes -6, 9, 3, all over root 14 times root 14. And so let's rewrite this. What we're going to do is we're going to divide each of these components by 14. And this will give us -6 over 14, 9 over 14, and 3 over 14. One more thing, let's just simplify this fraction. Only one of these fractions can be simplified, but this first fraction can be simplified to -3 over 7. And we'll leave the other components the same. And so now this is our vector projection. So this is the vector projection of B onto A. Okay, finally one more practice problem involving this application of work. Now, in your physics class, or a lot of other maths before this, I think we've talked about these applications in both Calculus 1 and 2. Just briefly, we learned that work is equal to the force times distance. So the work done is by this constant force, and the distance an object has been moved. However, this goes under the assumption that the force and the direction that the object is moved is the same. So if we have some object and we are putting some force on the object and it moves a certain distance, D, then this is a fairly simple problem. But in most cases, our force is actually not in the exact direction of the object's movement. So say we're dragging something, and we're dragging this object, and our force is actually at some angle. If we are, for example, pulling a wagon, we might actually be pulling it up as we're trying to move this object forward. So, if our force is in the vector PR, so this is the vector for our force F, and we are moving an object this distance, well, then the work is just going to be the horizontal component of this force. Because the vertical component of this force doesn't factor in, we're moving this object forward. So we are taking the horizontal component of this force, which is the magnitude of that force times the cosine of the angle, and we're multiplying it by this distance to get work. So we have this equation here. And now we also know that, well, if we rearrange this equation, we can just get this magnitude of force times magnitude of distance times cosine of theta. We're just manipulating this. But what does this look like? Well, this looks exactly like our dot product. And we're going back to that grand equation that says that the dot product of vectors A and B is equal to magnitude of A times magnitude of B times the cosine of theta. So this is the same formula. We're just applying it to problems done with work. So let's look at this example. A wagon is pulled a distance of 100 meters along a horizontal path by a constant force of 70 newtons. The handle of the wagon is held at an angle of 35 degrees above the horizontal. Find the work done by the force. So what that looks like is we have some wagon, and it is pulled a distance 100 meters along a horizontal path. It's pulled by a constant force of 70 newtons, and the handle of the wagon is held at an angle of 35 degrees above the horizontal. All right, so we have the force which has a magnitude of 70 newtons, and it is held at an angle of 35 degrees above the horizontal. So we want to find the work done by the force. Well, we have this equation here that says work is the magnitude of the force times the magnitude of the distance times the cosine of theta. And we have everything we need in this problem. That work is equal to the magnitude of the force, which is 70 newtons, times the magnitude of the distance, which is 100 meters, times the cosine of theta, which is 35 degrees. Kind of a plug and chug from here. So the work is going to be 70 newtons times 100 meters times the cosine of 35 degrees. And plugging this into our calculators, we get that the work is equal to 5,734 Newton meters. And what is a Newton meter? Yes, it is joules. So the work is 5,734 joules. A joule is just what we call a Newton times a meter because it's the common unit for work. All right, example 9. We do have one more example. I'm sorry, I keep saying last example, but this is the last problem. So, a force is given this time by a vector, 3i plus 4j plus 5k, and moves a particle from this point P to the point Q, and we want to find the work done. And now we have a hint that we're probably going to use the dot product version of this formula, because in this case we have a vector for f. In the problem above, we couldn't use that dot product because we did not have a vector for f. We had a direction and we had a force, but we didn't have the vector. We would have had to find the vector, which we could do, but it was easier to use this version of the formula. In this case that we do have a vector that we're given, we don't need to find that vector, then we can just go ahead and use that dot product. So we already have F. So this vector F is equal to, and I'll just rewrite this as 3, 4, 5. Okay, now what is D? Well, D is equal to the distance from P to Q. I'm sorry, not the distance, but the vector from P to Q. So I can really say the vector D is the same as this vector PQ. How do I find this vector PQ? Well, I'm taking all of the points of Q and subtracting from them P. So all components of Q and subtracting P. So I've got 4 minus 2, 6 minus 1, 2 minus 0, which is equal to the vector 2, 5, 2. So now to find the work done, we're just taking that force vector and finding the dot product of that and the distance vector. So we're taking the dot product of 3, 4, 5, and 2, 5, 2, which will give us 3 times 2 plus 4 times 5 plus 5 times 2, which is 36. And because we're not really given any units, we can just say that this is 36 units. All right, that is it for the dot product. Thank you for watching this video and have a great day.